Assalamu alaikum wa rahmatullahi wa barakatuh. Today is our lecture 25, and in the previous lectures, we are discussing about the continuous random variable, and we will continue today with the topic of families of continuous random variables. So as we have seen in the previous chapter with the discrete random variables, and we defined the families of discrete random variables, we have seen that the advantage of defining or these families of random variables is that most of the experiments they exhibit the same nature, and based on their nature we can put them in a certain family, and the benefit of that is that they have the same mathematical formulation, and that formulation helps us means with the well-known analysis which are already being carried out, so we don't have to go through long calculations to perform each and every test. So that's the advantage, the same that we will get in the for the continuous random variable. So for the first family that we are going to define with the continuous random variables is the uniform random variable. So the uniform random variable we define is x is uniform AB random variable if the PDF of x is f small f, so we use this symbol small f sub x of x is equal to 1 over b minus a for the range of this one a to b, and sorry it's 0 otherwise. So where parameters b is greater than a. So in that case, in simple, it's a uniform. Uniform means that all the values in the range of a and b, their probability will be the same, and that probability will be 1 over b minus a. And the theorem that is defined for this uniform random variable, it is defined as theorem 4.6. It says that we can have the CDF because it's a continuous random variable and it's the family of uniform random variable. So we can have the CDF of x is then simply defined as, so the CDF of x is defined as fx of x is equal to 0 for x is less than equal to a, x minus a over b minus a for x is less than equal to b and greater than a, and it is defined 1 for x is greater than b. Similarly, the other parameters that of interest for us is the expected value of x, so it is defined as b plus a over 2, and similarly variance of x is defined as b minus a whole square by 12. So we don't need to prove them for all these values for this uniform random variable. So let's look at an example to better understand how we can utilize these formulas to calculate all these values. So let's paste it from the book. So this is example 4.11. So it says that the phase angle capital theta of a signal at the input to a modem is uniformly distributed between 0 and 2 pi radians. So what are the PDF, CDF expected value and the variance of theta? So this is pretty simple. The PDF is defined as uh, small theta, and it is equal to 1 over b minus a. So this is b and this is a. So 1 over b minus a, 1 over 2 pi minus 0, 1 over 2 pi, and that is in the range of theta less than 2 pi greater than equal to 0, 0 otherwise. So we have this PDF defined. So CDF also we can define using the theorem that we have seen. F theta of theta is equal to, so it's defined 0 for x is less than or equal to a, and x minus a, x is here, sorry, theta is uh, theta is less than or equal to a is here 0, and x minus a, which is theta minus 0, theta over b minus a, 2 pi minus 0, so 2 pi. So this is in the range of theta is less than or equal to 2 pi greater than 0, and that would be 1 for theta is greater than 2 pi. Similarly, we can find out the expected value of x, which is theta here, expected value of theta. So that would be defined as b plus a over 2. So b is here 2 pi plus 0 and divided by 2, which is pi. So this is the expected value or the average value. Similarly, variance can be calculated as variance of x, which is defined as b minus a whole square. So b is 2 pi minus a whole square, a is 0, so divided by 12. So it is 4 pi square by 12, so which is pi square by 3. So we have seen that because of this, it is a family of random variable, uniform random variable. So it's quite easy to analyze to find out its CDF, to find out if its expected value and the variance, so that we can analyze how our however this uniform random variable is behaving. Similarly, we can find out the this is theta, the standard deviation, so that will be square root of pi square by 3, which is pi over square root of 3. So the next family of random variable is exponential random variable. Exponential random variable. So exponential random variable is it is relative to the geometric in the discrete random variables. So in the geometric, if we just recall that geometric random variable, we have seen that we will do the Bernoulli trials until we get our first desired success. So or the first desired result, whatever. So this is the same concept will be applied here, but now this is for the continuous random variable. So we say that x is exponential, x is exponential lambda random variable if the PDF of x is defined as fx of x is equal to lambda e raised to power minus lambda x for x is greater than equal to 0 and 0 otherwise. So similarly, we can have a example of this, or we can define its properties first as the theorem 4.8, and then we look at its example. So theorem 4.8, it says that if x is an exponential, if x is an exponential, lambda random variable, so then the CDF is the CDF of x is defined as fx of x equals to 1 minus e raised to power minus lambda x for x is greater than or equal to 0, 0 otherwise. Similarly, the expected value of x of exponential random variable is defined as 1 over lambda, and the variance of exponential random variable is defined as 1 over lambda square. Okay, so let's look at the example. So it's example 4.12, and it says that the probability that a telephone call lasts no more than 3 minutes is often modeled as exponential CDF. So we have given this exponential CDF f of t, which is 1 minus e raised to power minus t by 3 for t is greater than or equal to 0, 0 otherwise. What is the PDF of the duration in minutes of a telephone conversation? So from CDF, finding the PDF is quite straightforward. We just have to differentiate this CDF to calculate this PDF. So that would be straightforward. So if we differentiate it, this would be 0. So this minus minus plus, and this will be 1 over 3 e raised power 1 over 3 e raised power minus t by 3 for t is greater than or equal to 0, and this is 0 otherwise. So now that is quite simple to find out this PDF. Next, what it says that what is the probability that a conversation will last between 2 and 4 minutes? So what was the probability that it lasts between 2 and 4 minutes? Okay. So before doing the second part, let's plot this thing. That is quite simple. Again, I will suggest you must you must calculate some points to plot it exactly, but I will just draw its shape. So it's actually negative exponential, so it's a decaying function. So this is at 0, it would be some value, so it should be a dotted line here, but that's okay. Now this is how it can be done. So what is the probability that a conversation will last between 2 and 4 minutes? So we need to find the probability of so that it's lasts between 2 and 4 minutes. So from PDF, from CDF, it can be easily find out f4 of 4 minus f2 of 2, which is equal to, if we just put that values there, it would be minus 2 by 3 minus e minus 4 by 3, so it would be 0.250. So that's quite simple. The next example is the continuation of this example, for example 4.13, and it asks us to find out the expected value of t. Example 4.13. So we can solve this, we can find out this expected value as we have done in the previous lecture by using the uh, formula of which is defined as minus infinity to infinity t f t of t dt. We can use this relation, but it is for the relation where we don't know what kind of family that this random variable belongs to. But here we can figure out that f of t, the PDF is belongs to the exponential random variable with lambda is equal to 1 by 3. So we can say that t is exponential with lambda 1 over 3. So in that case, we have this relation, we have this theorem that we have defined earlier as theorem 4.8. In that case, expected value of x would be simply 1 over lambda, which is 1 over 3, which is 3. And the variance of x would be straightforward 1 over lambda square. So that would be 9. So that's easy. We can even use the integration by parts by using this relation, and we can find out the variance also by using that relation. So we can use the relation to find out these expected value. So we can do that also from minus infinity to infinity t f t of t dt. So that would be from 0 to infinity t 1 over 3 e raised to power minus t by 3 dt. So the shortcut that we have seen that means we use derivative here and integral here. So 1 by 3t, and we will use integration for here. So that would be 1 by 3 minus minus 3 e raised to power minus t by 3. That would be 0, and that would be 9 e raised to power minus t by 3. And we use the sign plus minus plus and so on. So that would be multiplied here, and that would be, so that would be minus 3 into 1 by 3 is minus t e raised to power minus t by 3. So this is minus 3 e raised to power minus t by 3 uh, over the interval of 0 to infinity. So this term will straightforward goes to 0. So for infinity this would be minus for infinity it would be 3 e raised to power minus t minus infinity, which is approximately 0. So that will be 0 minus e raised to power 0 is 1. So that will be simply 3. So it will be 3. So that is the same that we have find out using the direct relation. Similarly, we can find out the variance, but for the variance we need to variance of this t, we need to calculate the second moment of t minus square of the first moment. So we need to calculate the second moment. So second moment of that would be simply 0 to infinity 1 over 3 t square e raised to power minus t by 3 dt. So we will use the same shortcut method to find out. So here we will write derivative, here we will write integral, and here we will use the sign plus minus and so on. So that will be 1 over 3 t square, and that will be raised to power minus t by 3. So that would be simply 2 by 3t, and that would be minus 1 over 3 e raised to power minus 3 e raised to power minus t by 3. That would be 2 by 3, and that would be 9 e raised to power minus t by 3, and then it would be 0, it would be 27 minus 27 e raised to power minus t by 3. So same plus minus, so that would be here, here, and here. So that integral would be simply t square e raised to power minus t by 3. That would be plus minus, that is minus, and it would be 3 2s are 6 t e raised to power minus t by 3, and that is minus 9 2s are 18. Okay, and that is e raised to power minus t by 3 for the over the range of 0 to plus infinity. So for this range, this term is 0 straightforward, this term is straightforward 0. So we are left with minus 18 e raised to power minus t by 3 uh, 0 to infinity. So if you put infinity, it would is 0, and for 0 it is plus 18. So that would be 18. So variance of t would be then 18 minus expected value of t square. So that is 18 minus 9, which is 9. So that's the same that we have seen with the direct relation that is defined in the theorem 4.8. So the next family of random variable that we will be seeing in this uh, lecture is Erlong random variable. Erlong random variable. Erlong random variable is approximately the same in the discrete random variable as the Poisson random variable, in which we have seen that the time is involved. So is an Erlong n sorry n lambda random variable if the PDF of x is fx of x equals to lambda power n x n minus 1 uh, e raised power minus lambda x divided by n minus 1 whole factorial for x is greater than or equal to 0, 0 otherwise. So that is quite straightforward. For the parameter lambda should be greater than 0 and n should be greater than or equal to 1 and should be an integer. So here obviously the theorem is defined as theorem 4.10. It says that the expected value of x of Erlong random variable is n over lambda if x is Erlong n lambda, and the variance is defined as n over lambda square. So we don't have to go along integration and everything to find out these properties. So let's look at an example, and it is quiz 4.5 from the book, and it says that continuous random variable x has expected value of x is given as 3 and variance is given as 9. Find the PDF fx of x if x is an exponential random variable. So that's a straightforward reverse engineering. So for exponential random variable, we know that expected value of x is 1 over lambda, so which is equal to 3, which implies that lambda is equal to 1 over 3. So we can write fx of x, which is equal to then 1 over 3 e raised power minus x over 3 for x is greater than or equal to 0, 0 otherwise. So similarly we can use uh, this was part A, and the part B says that x is continuous uniform random variable. So for the uniform random variable, we know that expected value of x is defined as a plus b over 2, which is equal to 3, and variance of x is defined as b minus a whole square by 12, which is equal to 9. So now we have two equations and two unknowns, and we have to find out the b and a for this relation. So I will leave this calculation for you people to do. So we can find out b b here is 3 plus 3 square root of 3, and a is equal to 3 minus 3 square root of 3. So what would be then fx of x would be straightforward 1 over b minus a, which is 6 root 3, for x is 3 plus square root 3 and 3 minus square root of 3 times square root of 3. So 0 otherwise. Similarly, C part says that x is r long. So for r long, expected value of x is defined as n over lambda, which is 3, and variance of x is defined as n over lambda square, which is 9. So we have to again calculate two parameters n and lambda. So from here we can see that n is equal to 3 lambda, and from here n is equal to uh, lambda square 9. So sorry. So it is n is equal to 3 lambda is equal to lambda square 9. So from here we can see that lambda is equal to 1 over 3, and n is equal to 1. So as a result, the r long would be then fx of x for n is equal to 1 and lambda 1 by 3. So it is 1 over 3 e raised power minus x by 3 for x is greater than or equal to 0, 0 otherwise. So I hope you have understood these families of random variables. We will continue with these families of continuous random variable in the next lecture. Stay blessed. Assalamu alaikum wa rahmatullahi wa barakatuhu.